Okay, so here's what we're going through. The figure shows a tank open to the atmosphere and filled to a depth D with a liquid of density rho L suspended from the string as a block with density PB or rho B, which is a bit more dense, whose dimensions are XYZ. The top of the block is H below the surface of the liquid. So what we're going to look for first is we are going to find the force due to the pressure on the top surface of the block and the bottom surface. Sketch these in the diagram below. All right, let's do it. So to figure out the force, we're going to first figure out the pressure. So let's do pressure of the top. There's a formula you got for this. It is rho GH. Now, which rho is this? This is the density of the liquid. So that's that. But we want to know what's the force. So what you got to keep in mind is pressure is equal to force over area. So that means that force is equal to pressure times the area. We're going to be doing that a lot here. So here's my pressure. All I got to do is multiply by the area. What's the area of the top? Well, the area of the top is going to be a rectangle. And in case you forgot the formula, it's going to be x times y. So the force on the top is equal to xy rho LGH. And you're done. Perfect. We're going to do the same kind of thing for the force on the bottom. So the pressure on the bottom is going to equal rho L because you're in the same liquid, G because you got the same gravity, but you are further in the water. How much further? Z further. So H plus Z. And that's it. But we need to know the force. So the force for the bottom, well, what's the area of the bottom? Well, the area for the bottom is going to equal the area on the top. So it's just going to be xy rho L G parentheses H plus Z. And that's it. So sketch these forces in the diagram. Boom, there's the force bottom. And where's the force top going to be? Boom, there's the force top. Which one's bigger? The force bottom is bigger. Nice. Moving to the next one. What are the average forces due to the pressure on the other four sides of the block? All right, well, since it's a rectangle here, we got two different sides. Let's worry about this guy first. We'll call it the front. So we'll call it force front. Now, this is going to equal the pressure times the area. So let's just do the area real quick here. It's going to be YZ times the pressure. How far down is it? Well, it's going to be rho L times G times the middle here, right? So that's what it means by average. If you're into calculus, this is a good integral problem, but we're not doing that today. So it is going to be H plus Z over 2. That is going to be the force on the front of the block. Gorgeous. Now, there's another side here. We are going to figure out the force on the side. By side, we're talking about this guy right there. It's going to be almost the same, but it's got a different area. It's a Z and an X, so we'll say it's XZ times rho LG. How far down is it? Well, the middle of it is going to be H plus Z over 2. Bada bing, bada boom, and those are your two sides. I don't have the picture on this one, but, you know, here's your F side. And then for green, here is your F front. Now, your back is going to be exactly the same as the front, and your two sides are also going to be identical as well, so we don't need to figure out all four of them. But you can if you're into that kind of thing. All right, looking at the next one, what is the total force? By total, they're talking about net force because, yeah. All right, so things we know. This guy and this guy are going to cancel out. They're the same. They're opposite directions. Nobody likes people like that. This guy and this guy are going to cancel out because they're lame. Which two are the only two that are going to survive? The top and the bottom, because these ones are not the same and they won't cancel out. So what we're going to do is we are going to subtract them because they're going opposite directions. So your force net is going to equal, I'm going to put the bottom one first because I know it's bigger. So a second ago, well, let's just write force bottom minus force top. And that's what we're doing. So force on the bottom was X, Y, rho, L, G, parentheses, H plus Z. And we are going to subtract the top, which was X, Y, rho, L, G, H. Just the H. Nice. Okay. Hey, that is good. You're all set for that. But what I'm going to do is I am going to use hindsight and simplify this just a wee bit. Now we both terms have a xy rho g, xy rho g. I'm going to factor that out. So I am going to get an xy rho l g, and then we're going to have h plus z minus h minus h. Ta-da! Well, h minus h takes each other out, so we're going to have an x, y, rho, l, g, z. Nice. So this is our force net. Beautiful. So if you didn't do that on this step, that's okay, but you're going to want to do it for this next step here. Find an expression for the buoyant force on the block. Well, we have a formula for that. Your force of buoyancy is going to equal rho VG, right? Now, rho, we know, is just the density of the liquid, not the block, times the volume. Well, it's a nice old rectangular prism, so XYZ times G. Now, what you should notice, how does it compare to your answer in part C? It's the same. Ta-da! It's the same because the net force is equal to the buoyant force. Okay, let's keep trucking. What is the tension on the string? Most interesting question, I think, but whatever. So let's draw a free body diagram. You have gravity, you have Fg pulling it down, you have your buoyancy force pushing it up, Fb, and then you have the tension on the string that's filling in the gap, right? So these two, the top two add together to get the bottom two. So that means that the force of tension is going to equal the force of gravity minus the force of buoyancy, which should make sense. The less buoyant it is, the more tension there's going to be. Now we have a formula for all of these wonderful situations here. So Fg is going to equal m times g minus rho liquid x, y, z, g, which is what we just got from the previous question there. Now, mg, we can work through here. We know that density is equal to mass divided by volume. Kick the volume over, volume times density, is equal to m. That's a rho, not a p, in case you can't tell. Well, I wrote a p, I'll admit it. Anyways, so your force of tension is going to equal our volume times our rho times our g minus this same fella right here who doesn't change. Now, looking at this volume here, we know how to calculate that. So our force of tension is going to equal x, y, z. This rho, we should label it. We forgot to put a label on there. This is the density of the block itself. So we're going to put B right there. G minus rho L x, y, z, g, which is great. Now we can simplify this a little bit. They both have x, y, z. They both have a g. So we're going to factor those puppies out. So your force of tension is going to equal x, y, z, g. And then in parentheses, rho b minus rho l. And that is it. Too easy. easy, right? See you next time.